Hello boys and girls, welcome back to CubeRoot Learning, and in this video we'll be learning about class 10 chapter number 1 real numbers, and we'll be learning about fundamental theorem of arithmetic. We'll be learning how to find HCF and LCM using prime factorization, and also we will be solving exercise 1.1. So let us start. First let us learn what is the fundamental theorem of arithmetic. One thing I want to say is you don't have to buy hard this thing, just need to understand what it is. They are not going to ask what's the definition of fundamental theorem of arithmetic for examination. You just need to understand the concept. Okay. So let me read it out. Every composite number can be expressed or factorized as a product of primes, and this factorization is unique apart from the order the prime numbers occur. So, in a simplified sentence, if I explain, what they're trying to say is that every composite number can be expressed as a product of prime numbers. And this factorization is very unique that just the order of the primes only change. Other than that, when you do a prime factorization of a number, it's always unique. A number can be expressed in terms of product of primes only in a one particular way. Yes, the order can change. Other than that, whatever you're getting the product of primes, it's always unique. That is what they're trying to. So in order to write a composite number in terms of prime numbers, you should do prime factorization, right? So before knowing what is prime factorization, you should know what is prime numbers. I've already written over here what is a prime number. Prime number is a whole number that is greater than 1 and which is divisible by 1 and the number itself. That is the definition of prime number. If you're wondering, I'll explain you over here. 2, right? 2 is divisible by 1. Actually, all numbers are divisible by 1. You don't have to check that. Then 2 is only divisible by 2 itself, right? Is there any other number that 2 is actually divisible? No, right? So it's 2. It's a prime number. Same for 3. 3 again. It's 3 is only divisible by 3 itself, right? And 1, of course. Other than that, is there any other number that is 3 is actually divisible? No. Right. Or does 3 have any other factors apart from this? 3 only have two factors, that is one factor is 1 itself and the other factor is the number itself, that is 3. These are the factors of 3, right? For 2 also same. So prime numbers are basically nothing but they only have, what do you say, two factors, that is the number itself and 1. So that is what is prime numbers. So what about composite numbers? The numbers which are not prime, they are composite numbers in simple language. But if you want a proper definition, it simply means that numbers having more than two factors. Take 6 and 20 over here. To do the prime factorization of 6 and 20, 6 I have written here. I'll take 2 first. So 2 3s are 6, right? So 3 comes over here. Then 3 ones are 3, right? So we'll get the prime factorization as 2 into 3. 6 can be expressed in the terms of primes. So 6 is a composite number. Not only that, 6 have more than two factors, right? 6 is divisible by 1, 6 is divisible by 3. 6 is divisible by 1, 6 is divisible by 6, 6 is divisible by 2, it is divisible by 3. It have more than two factors, right? So 6 is a composite number, and expressing 6 is a composite number, and expressing this in terms of prime numbers is called fundamental theorem of arithmetic. Same for 20 if I take. Not only that, if I take 6, first I'm doing prime factorization with 3. So 3 into 2, 6. So 2 comes here. Then 2 comes here again. So 6 can be only expressed in terms of prime, that is 2 into 3 or 3 into 2. Other than that, no other way you can express 6. That is what fundamental theorem of arithmetic explains. So if you take 20 here, I'll first do the prime factorization with 5. I'll get 5 4s are 20, so 4 I'll get here. Then 4, if I do it with 2 again, then I'll get it 2 here again, then 2 1. So I'll get 5 into 2 into 2, right? This is the prime factorization of 20, which is a composite number, right? So here this is the composite number over here, you have it over here, and this is your prime numbers. And expressing this in this term of prime composite number, which can be written as a product of prime numbers, is called fundamental theorem of arithmetic. Okay, so we'll be learning divisibility test. of the prime numbers mainly. Even composite numbers also have this divisibility test. But to do prime factorization, we'll learn about the divisibility test of the prime numbers. Because to do the prime factorization, I hope it's clear. Now we have 2 here, so the number should end with an even number. In order to check whether the number is divisible by 2 or can we do prime factorization with 2, in order to check that, you should know that the number should end with even number, right? If you take 100 over here, 0 is an even number, so it is divisible by 2. If you take 152, 2 is an even number, it is divisible by 2. If you take, what is it, 5, 6, 8. Again, it is divisible by 2 because the number is ending with an even number, right? What if it's a 5, 7, 5? It is not divisible because 5 is an odd number, not an even number. I hope it's clear. What about divisibility test for 3? Sum of digits of the number should be equal to the multiple of 3. For example, I'll have 2, 5, 6. So we'll add the digits of the number, sum of the digits of the number, that is 2 plus 5 plus 6, 13 I think. And 13 is not a multiple of 3, so 2, 5, 6 is not divisible by 3. I'll take another number, that is 108. When you add this digits, that is 1 plus 0 plus 8, you will get 1 plus 0 is 1, 1 plus 8 is 9, you get 9. So 108 is divisible by 3 because because 9 is a multiple of 3, right? So this number is divisible by 3. So and you can do prime factorization with this number. I hope it's clear. For 5, the number should end with 5 or 0. Okay. And for 7, there is no divisibility test. Just divided by 7 itself. Divided by 7, there is no as such of divisibility test for 7. And for 11, if you want, you can divide it by 11 itself and check the divisibility, whether you can do prime factorization with 11. You can check by dividing it with 11, the number with 11, or if I show an example over here. Here you have a number that is 1, 3, 2. Okay. I've named this number as 1, this is 2, and this is 3. Okay. I've written the number in the order 1, 2, 3. Okay. So here 1 is in the position of odd number. Here 2 is in the position of odd number, right? So here is, you just listen carefully. Here you have 1, 2, 3. I've just written the position of the numbers. Our real number is 132, but I have written the position of numbers as 1, 2, 3. If here 0 is also there, right here it as 4. Okay, hope it's clear. So now written like this. Here this 1 is in the position of 1, right, which is an odd number. Here this 2 is in a position of 3, which is also an odd number. I'm talking about the position, okay? Position 1 and 3 is an odd number. Okay, I hope it's clear. So what you're going to do is, you're going to add the numbers which is there in the odd positions. That is, you have 1 in the odd position, you have 2 in the odd position, right? So when you add, you have 1 plus 2, which is equals 3, right? You just have second position, which is in the even number position. So it is 3. So you have 1 plus 2 equals 3. Then you have 3 here. You don't have anything to add or subtract, right? Just 3. What you're going to do is, we're going to add, you added the odd number position, right? Now you have even number position. You have to subtract this. Even number position is 3. Odd number position is 3. So 3 minus 3 is what? 0. So what is divisibility test of 11? When you get 0 or when you subtract and you get 11, it means that the number is divisible by 11. I hope it's clear. Okay, even if it's not clear, it's fine. Just divide it by 11 to check whether it is divisible by 11. If you're getting the remainder is 0, then it is divisible by 11. So this is the divisibility test of 11. I hope it's clear. So what about HCF, right? The next topic is HCF, that is the highest common factor. So as per your syllabus, you have to learn to find HCF using the prime factorization method. Before teaching that method, I will be giving you a quick recap about the method that I've learned in your lower classes, right? How to find HCF. Even if you have forgotten also, it's fine. And if you did not understand also, it's fine, because we will be learning a new method, and that method is much more easier compared to the method which I'm going to show you right now. Just showing it as to give a quick recap. That's it. So what's HCF? HCF is highest common factor. When two numbers are given, the highest common factor that number has is the HCF. Okay. So I'll take the two numbers, that is have 24 and 36. Okay. I will find HCF of these two numbers using the old method, which is much more lengthier, which is the division method, probably called as the long division method, right? We'll write the bigger number in the place of dividend, and 24 is the divisor. So when you divide this, we will be writing the quotient over here. Okay. It's not on the top, we'll be writing over here. So 24, right? 24, when you divide by 36, 24 ones are 24, right? 24 twos are 48. You can't write twos are 48, right? You have to write ones are 24. So I've written 24 over here. So what is the remainder that you get? 36 minus 24. I think you will get 12. Then you will write this divisor in the place of here, which is your next dividend, and your remainder 12 will become your next divisor. Again, you'll write the quotient over here. Then that is 12 twos are 24, right? I've written 24 over here. You'll get here the remainder as 0. When you get the remainder as 0, which is your last divisor, that is 12, this is your HCF, which is 12, right? This 24 and 36 are all small numbers, so it's fine. You can do long division and find HCF and all, or maybe you can do some other method and all. But doing prime factorization is much more easier to find HCF, right? So for that, how to find HCF using prime factorization? I'll show you. We'll do the prime factorization of 24. So 24, you have twos are here, we'll get 12. Again, twos are, if you do, we'll get 6 over here, because 6 twos are 12, right? Then you do 2 here, again you'll get 3. Again you do 3, you will get 1, right? So 24 can be written as 2 into 2 into 2 into 3, right? Now what about 36? 36 I've written here. 36, again twos are 36. I think 18 twos are 36. Yes. Then you have 2 here again. You will get 9, because 9 twos are 18. Then you have 3 over here. 3 threes are 9. So you'll have 3 here. Again 3, 1. 36 can be expressed as 2 into 2 into 3 into 3. I hope this is clear. Now we need to find what's the HCF, which is the highest common factor. So you have to check what's common in 24 and 36. What is common in 24 and 36? You have 2 into 2 into 2 into 3. You have 2 into 2 and into 3 into 3. Right. So here you have 2. Here also you have 2. Here you have 3. Here also you have 3. So basically 2 and 3 are common. Right. So you see here carefully. Here 2 is common. Right. So I have drawn a box over here. Again 2 is common over here. Again I have drawn a box. Right. Then here 3 into 3, and here it is 2 into 2. 2 into 3, right? Here 1 2 is here, and here there is no 2, right? In 36 already I've drawn it inside the box. This 2 is not here. There is into 2 is not here, right? So you can't take that 2. Then what about 3? 3 into 3, yes. You have a 3 common over here, right? What about this 3? You can take this 3. Why? Because there is no into 3 extras in 24, right? Hope it's clear. We'll have 2. Then here we'll have again 2 into 3, which is 4 into 3, will be getting as 12. Okay, I hope this is clear. Once again, if you want, I'll explain. Here you see 24 can be expressed as 2 into 2 into 2 into 3, right? And 36 can be expressed as 2 into 2 into 3 into 3. We have to check the highest common factor. For that, you have to check the common factor between 26 and 36, right? Here you have 2, here also you have 2. In 26 also, in 36 also you have 3, 24 also you have 3. So we have common factors here, but how many common factors in general, right? So here you have 2 and 2, so we just pair them up. Again you have 2 and 2 over here, again you paired them up, right? Then you have 3 and 3, again you paired them up. Here you don't have any 2 to pair, and here you don't have any 3 to pair, right? Pair up. So this is, or when you take out the LCM, you'll get, I mean, when you take, sorry, when you take the HCF, that is 2 into 2 into 3, you will get 4 into 3, which is 12. I hope it's clear. You can write this as, there is 2 into 2 into 2, right? Which is 2, there are 3 times. So you can write 2 to the power 3. 2 raised to 3 into 3. And this you can write it as 2 into 2. So there are 2 raised to power 2, right? 2 raised to 2 into 3 raised to 2. Here it is 2 times are there. So we're writing 3 raised to 2, right? So when you write like this, as per your definition given in your textbook, when you take the highest common factor, what this is the definition given in the textbook, that is finding HCF, and LCM also have written. When we'll come to LCM, I'll explain about LCM. But just as of now, concentrate on HCF. The product of the smallest power of each common prime factors in the numbers. What does it mean? Product of the smallest power of each common factor. You can see the word common, right? Common prime factors in the numbers. What I've written is here. Here you have to check which is common. 2 is common for both numbers. 3 is also common for both numbers. Which has the lowest power? What about the lowest power? Here 2 raised to 3, here 2 raised to 2. So 2 raised to 2 is obviously the lowest power, right? So written here. Then 3 is also common. So which one is having the lowest power? Here it is 3 and 3 raised to 2, right? 3 is simply means 3 raised to 1 itself, right? So 3 raised to 1, that is 3 is having the lowest power. So it is 2 raised to 2 into 3. That is 4 into 3, which is 12. I hope it's clear what I'm trying to say. If you see, I have already told, no need to learn the definition by heart, just understand the meaning. For HCF, it simply means that you just have to find which is common between the two numbers. You have got common 2 and 3, right? And which is having the lowest power, write it down outside. Otherwise, if you find it difficult in doing in this power way and all, just simply write over here. I've told you, just pair them up and just take what's common outside. I hope it's clear. Now moving on to LCM, which is the lowest common multiple, right? So before teaching according to the prime factorization method, let us do the old method first. For example, if I take LCM for 6 and 8, right? So if you write multiples of 6, you have 6, you have 12, then you have 18, 6 4s are 24, 6 5s are 30, 6 6 are 36, then you have 42, 48, then 6 9s are 54, then you have 60, then 8. How will you write? Multiples of 8. 8 ones are 8, 8 twos are 16, 8 threes are 24, 8 fours are 32. I'm stopping till 32 because if you see the least common multiple, you have written the multiples of 6, you have written the multiples of 8. Which is the least common multiple of 6 and 8? You can see here 24 is here 8 is here, I mean here also 24 is here. So which is the least common multiple of 6 and 8? Which is LCM of 6 and 8 is 24, which is the least common multiple. When you write the multiples of 6, how do you write multiples of 6? Just write the table of 6. 6 ones are 6, you written 6 here. 6 twos are 12, written 12 here. Okay, you just wrote the multiples of 6, multiples of 8. Which is the common one, which is the least? The smallest common multiple of 6 and 8 is 24. So this is the much more lengthier method. For small numbers and all, you can just write the multiples and just take in the common one outside and all, it's fine. But what about bigger numbers come? It is difficult to write like this and just pick out the least common multiple. It's not easy. So we have to find it out using the prime factorization method. So now we will find the LCM of 6 and 8 using prime factorization. For that, I'll write 6 over here. Then I'll find the LCM of 6. We'll have 2 into 3 is the prime factorization of 6. For 8, 2 into 2 into 2. We'll write it in terms of power. That is 3 into 2, right? 8 will be writing as 2 raised to the power 3. Here it is basically 3 raised to the power 1 and 2 raised to the power 1 is basically means 2 into 3, right? Nothing else. So how to find the LCM using the prime factorization method, right? So if you see the definition over here, the product of the greatest power of each prime factor involved in the number. What they're trying to say is, here if you can see, the greatest power of the common factor. That is, here you have 2 is the common factor, right? You can see here 2 is the common factor, right? Its greatest power. So what? I've written LCM, that is 2 into, sorry, 2 raised to 3, which is the greatest power. And what's given here? Each prime number involved in the numbers. That is, you have to consider everyone. Here 3 is not common, but we will be taking 3 also for finding LCM. I hope it's clear. See, for HCF, we just have to take the common one outside, right, with the small power. But for LCM, you have to take all the numbers outside, and whichever common is there, you have to take its greatest power. We'll have 2 cube as 8, 8 into 3 is 24. So here we can see 6, that is 2 into 3, and 20 prime factorization is 2 into 2 into 5. So when you write in terms of power, that is 2 raised to 1 into 3 raised to 1 and 2 raised to 2 into 5. See, you don't have to actually write in terms of power and all. If you want, you just do it. If you don't want, you don't need to do it. Okay, but when you take the but the concept of HCF and LCM should be clear find by using the prime factorization. When you do more exercise questions, I hope it will be clear what I'm trying to say. What's HCF? The common number, common factor with the less power, right? If you want, see, you can see here. If you find it difficult in this power concept, see for HCF, 2 is common, right? I've taken the 2. Just paired this 2, right? Then is there anything else to pair? Nothing is there to pair. So HCF of 6 and 20 is 2. Here you can see 2 is the common factor and the smallest power is 1, right? 2 raised to 1 is the smallest power, so 2. So if you do in terms of power also, you can, if you find it difficult in terms of doing it power, you can pair it like this. That is 6 is 2 into 3 and 20 is 2 into 2 into 5. So this 2 just paired this out, and this rest of the numbers you can't pair it, right? There is nothing common and also you can't pair it. I hope it's clear. What about LCM? LCM, you have to take all the numbers, right? And whatever common is there, the highest number you have to take. So for here you can see, you have the common number as 2, right? So I've written 2 here. Then 2 is there more in this 20, right? That is 2 into 2. Again 2 is here. See, there are 2 2's here, right? Then take the rest of the numbers. Each of the prime factors is needed for this. I hope it's clear what I'm trying to say. In terms of power concept, if I explain, when you write the LCM, which common prime factor has the highest power, you just write it down. There's 2 raised to 2, right? So you just written 2 into 2. Then whatever is remaining also you will write. Whatever common is there, you will take the highest value outside, and whatever remaining you will write. So when you write the LCM of 6 and 20, that is 2 into 2 is 4, 5 3 is 15, so 4 into 15 is 60. So LCM of 6 and 20 is 60. I hope it's clear. Another concept that you have is LCM and HCF. You found out, right? So when the HCF of two numbers into LCM of two numbers equals the product of two numbers. When you found out the HCF of two numbers and LCM of two numbers, the product of HCF and LCM is equal to the product of the two numbers. So here HCF of 6 and 2 into LCM of 6 and 20 is 2 into 60, right, which is 120. What about the product of two numbers, that is 6 into 20? Again, you'll get 120, right? So these two are equal. I hope it's clear what I'm trying to say. Now let us move on to exercise 1.1 of this chapter. And the first question says express each numbers as the product of its prime numbers. You have to do the prime factorization, then express it in terms of prime numbers. So for that, here you have first number as 140, right? I've written 140 over here. We'll do the first we'll do the prime factorization with 2. You have 2 over here. 2 sevens are 14, so we'll have 7. Then 0. Again we'll do it in, we'll have 2 threes are 6. We have a remainder 1, which will make it as 10. So 2 fives are 10, we'll have 35. Then we will take it as 5 as the next number. 5 sevens are 35, we'll have 7 here. Okay. So when you will write 140 in terms of prime numbers, we'll have 2 into 2 into 5 into 7. This is how we express 140 in terms of prime numbers. Now let us move on to the next question. That is, next question is, which is part 2. That is, you have to find the prime factorization of 156. I'll do it with 2. So listen carefully. 2 sevens are 14. You have a remainder 1, which will become 16, and 2 eights are 16, right? You have 78. Again, we'll have 2 over here. Then 2 threes are 6. We'll have a remainder 1, which will become 18, and 2 nines are 18. So we'll have 39, right? This number is divisible by 3, right? If you check, 3 plus 9 is 12. 12 is a multiple of 3. It goes in 3's table. So we've done 3 here. 3 ones are 3. Then you have 9. 9. 3 threes are 9. So you'll have 13. 13 is a prime number. So you have 1. So 156 can be expressed in terms of prime, that is 2 into 2 into 3 into 13. Now we have next question, that is 3, 8, 2, 5. First we'll check the divisibility of 5, right? It is divisible by 5. So we'll do the prime factorization with 5. So 5 is what? 38, right? So 5 sevens are 35. So we'll have a remainder 3. Then that will become 32. So 5 6 are 30. Again reminder, you will have 2 and 5. 25 it will become. So 5 5s are 25. So we'll have 765. Again we'll do it with 5. 5 ones are 5. Reminder 2 you will have. So it will become 26. So 5 5s are 25. We'll have reminder 1 15. Then 5 3s are 15, right? So we'll have 153. If you see 153, right? 1 plus 5 plus 3, you will get it as 9, which is the multiple of 3, right? So it will go in 3's table. So when you do it 3, 3, 5, 5s are 15, right? So look at 5, then 3 ones are 3. We'll have 51. Again, 5 plus 1 is 6. 6 is a multiple of 3, so it will go in 3's table again. So we'll have 3 here, then 51, right? So 3 ones are 3. You have a remainder as 2, then that will become 21. So 3 sevens are 21. We'll have 17. 17 is a prime number. So yes, 3, 8, 2, 5 can be expressed as 5 into 5 into 3 into 3 into 17. I hope this is clear. We have the next number, that is 5005. Since it's ending with 5, it is obviously prime factorization. We can do it with 5, right? We'll have 1001. 1001. It is not divisible by 2, not divisible by 3, not divisible by 5. What about 7? You have to divide and check whether it is divisible by 7 or not. So 143 it will go in 7's table, so it is divisible by 7. About 143, right? Is 143 again going in 7's table? We'll check. We'll get a reminder as 3, so it is not going in 7's table. What about 11? We have a divisibility test for checking whether it goes in 11's table or not. If you want, you can divide and check. Otherwise, you can see here. I have 143, right? I am positioning this number. This is 1, first position, second position, third position. Now I have to find the sum of the digits in the odd position. So odd position, sum of digits, that is 1 plus 3, which is 4. And sum of the digits of the even position. There is nothing to add for even position because there is only one even position, so the sum is 4 itself, right? So what is the difference of 4 minus 4? It is 0. So this is divisible by 11. This 143 number is divisible by 11. you'll have 13. 13 again is a prime number, so 1. So 5005 can be expressed in terms of prime numbers, that is 5 into 7 into 11 into 13. 7429, and you have to check in which table will it go, right? So it will not go into, you cannot do prime factorization with 2. What about 3? 7 plus 4 is 11. 11 plus 2 is 13. 13 plus 9 is 22. So it is not divisible by 3 also. 5 also not divisible. What about 7? We'll check whether it is divisible by 7. 7 ones are, so it is not divisible because we'll get the remainder as 2. So it is not divisible by 7. What about 11? We'll position the numbers, that is 1, 2, 3, 4. Some of the digits in the odd position, that is 7 plus 2. We'll get it as 11. Then some of the digits of the even position, that is 4 plus 9. 4 plus 9 is 13. When you subtract, you will not get it as 0 or 11. So this is also not divisible by 11. Okay, now what about next number is 13, right? So 13 you have to check whether long division. When you subtract, you'll obviously get a remainder, so it is not divisible by 13 also. 15 you don't have to check because 15 is not a prime number. Next is 17. We have to check whether it will go in 17 stable or not. So it will go in 17 stable, right? We'll have 437. Now you have to check this 437 goes in 17 stable or not. Not goes in, no, this will not go in 17 stable. Will not get the remainder 0. After 17 you have 19, right? Check whether it will go in 19 stable or not. That is 447, 19, right? So we'll have 0. So this will go in 19 stable. It is divisible by 9. You have 23. 23 again is a prime number. So 7429 can be written as 17 into 9 into 23. I hope this question is clear. The first question is over. Second question, find HCF and LCM of the following of the integers and verify that HCF into LCM equals product of the two numbers. Okay. So for that, first you need to find the prime factorization of 26 and 91. So for 26, prime factorization is, with the 2 if you do, we'll get 13. 13 here is 1. And for 91, we'll get 13 over here. Then 13 here again, 1. 13 sevens are 91. Okay. So 26 can be written as 2 into 13 and 91 can be written as 7 into 13. So what is the HCF of 26 and 91? You know that 13 is common, so when you will pair this up, HCF is 13. And LCM of 26 and 91 is what? You have 13 commons, you have written 13 over here. Then rest of the other whatever prime factors are there, you have 2 into 7. You have to check whether this product of these numbers are equal or not, right? With the product of HCF and LCM. So for that, you have to multiply 26 into 91. 26 into 91 is 2366. And you have to multiply the HCF into LCM, right? That is 13 into 182. That also you will get 2366. So these two are equal. Prime factorization of 5, 10 and 92. Right. First we'll do it with 2. 2 2s are 4. 1 you have. So 1 11. So 2 5s are 10, right? Again 1 will have. Then it will become 10. Then 2 5s are 10, right? So we'll have 255. Then into 5 we will do, since it is ending with 5. 25, right? 5 5s are 25. Then you have 5 1s are 5. So 51. So prime factorization of 510 is 2 into 5 into 3 into 17. For 92 you need to find it out. 2 4s are 8. So remainder will have 1. Then it will become 12. 2 6 are 12. 46. Again you will do it with 2. 2 2s are 4. 2 3s are 6, 23. Then you will have 23. So 92 you can be written as 2 into 2 into 23. So HCF of 510 and 92 is what? You have a 2 common here, right? You have taken the 2 common outside. If you want to see it in the power method as per the definition, I will show you. You have 2 into 5 into 3 into 17, right? Here you have 2 raised to 2 into 23. So here 2 is common, 2 is common, but with the lowest power for HCF. So you have taken 2 with the lowest power, right? 2 raised to 1 is 2 itself. So 2 is HCF. Otherwise, you can just pair this out and take. What about LCM? For finding LCM of 510 and 92, you can see here 2 is common, right? And with the highest power, that is 2 raised to 2. So written 2 raised to 2 over here. Then whatever is remaining, you will write. Yeah, 5 into 3 into 17 into 23. When you multiply this, 23460 will get it as this. Okay. Now you have to check the product of HCF and LCM on the product of the two numbers, right? So when you multiply LCM into HCF, you will get 46926, and you multiply 510 into 92, again you will get 46926. I hope this question is clear. Going on to the next question, that is 336. We have to find the prime factorization, right? I'll do it with 2. That is 2 ones are 2, then you have 1, it will become 13, then 2 6 are 12, again reminder 1, then that will become 16, 2 8s are 16. So you have 168, right? Then again with the 2 we'll do. So we'll have 2 8s are 16, then 2 4s are 8. Again with the 2 we'll do, that is 2 4s are 8. 336 can be written as 2 into 2 into 2 into 2 into 3 into 7. That is 2 raised to 4 into 3 into 7. Right. Now for 54, when you do, so 54 can be written as 2 into 3 into 3 into 3 is equal to 2 into 3 raised to 3. Listen carefully here. We need to find the HCF and LCM, right? So HCF and LCM you have over here. We have to find it out. LCM you can take the common outside, right? Pairing and taking it outside. 2 is common here, so taken 2 here. Then 3, then this 3 is here, so you're taken common 3. So it is 2 into 3, this is 6, is the HCF, right? If you check in the terms of power, here you have 2 common is there, 3 is common is there. 2 with the lowest power, you have taken 2, 3 with the lowest power, you have taken 3, so 2 into 3 is 6. What about LCM? LCM, for first, for the common numbers, take the highest power outside, that is you have 4, 2 is common, so we'll take 2 raised to 4, and 3 is also common, we'll take with the highest power, that is 3 raised to 3 into 7. So when you multiply and see, what will you get? 3024. And HCF into LCM, when you multiply and see, you'll have 6 into 3024. When you multiply the products, that is 336 into 54, right? Same only you will get 18144. Since the examination calculator is not allowed, don't simply copy what is there in the screen, just multiply, you got this answer. No, make sure you do it with a pen and a paper, so that it will be much more practice. During the examination also you can do calculation much more faster. Now this is the third question, and you have to find HCF and LCM of the following integers by applying the prime factorization method. Okay. So for 12, right, when you do the prime factorization of 12, it can be written as 2 into 2 into 3. For 15, prime factorization is 5 into 3. 21, prime factorization is 7 into 3, right? So you need to find the HCF. You can see 3 is common, right? So I've taken the 3 outside, so HCF is 3. What about LCM? LCM, we'll first write what is common with the highest power. 3 is common with the highest power, that is 1 itself. So 3 you will write it only one time. Okay, I've taken the 3 which is common, write it only one time. Then rest you have 2 into 2, then you have 5 into 7, right? So what will you get? You'll get the LCM as 420. I hope this question is clear. Now this is the second part. 17, when you do prime factorization, you will get 17 into 1. 23 also will have 23 into 1. 29, when you write, you'll have 29 into 1. So which is what's the HCF? We can see here that is 1 into 1 into 1, right? 1 is the HCF, which is the highest common factor. And what about LCM? So LCM, when you will write, we have 17 into 23 into 29. When you multiply this, you will get 11339. The next question, this is you have to find again HCF and LCM, right? For that, we'll write the prime factorization, that is 8 you can write it as 2 into 2 into 2, and 9 you can write it as 3 into 3, and 25 you can write it as 5 into 5, right? And what's common? 1 is the highest common factor over here, right? So HCF is 1. What about LCM? LCM is 2 into 2 into 2, then you have 3 into 3, then you have 5 into 5. When you multiply this, you will get 1800. I hope this is clear. In this question, it is given that HCF of two numbers, that is 306 and 657, is given as 9. And they have asked us to find the LCM of these two numbers. See, you can actually find the LCM using the direct method. But in the question, it is given the value of HCF, right? And we have just learned a little before that. So we'll find the HCF. We know the HCF. We need to find the LCM, right? So we know the HCF is 9. Then into LCM equals product of two numbers, that is 306 into 657, right? So LCM will be equal to 306 into 657 divided by 9. When you cancel 9 and 306, you will get 34. Now you need to multiply 34 into 657. When you multiply, you will get the final answer as 22338. This is the final answer. So already in the question they have given the clue, they have given the HCF of two numbers, and you know the two numbers, and they are asking us to find LCM. Just do this method, that is HCF into LCM equals product of two numbers, rather than it is very time consuming of finding LCM of these two numbers, and you know the answer is a very big number, right? That is 22,338. So I hope it's clear. Now this is the fifth question. Check whether 6 raised to n can end with digit 0 for any natural number, right? The first point that you should keep in your mind is for any number to end with 0, it should contain the prime numbers. It should contain, right? I forgot to write contain. It should contain the prime numbers, that is 2 and 5. So when you write the prime factorization of 6, you know it is 2 into 3, right? You have a 2, but you don't have 5. So does it mean that 6 raised to n can end with the digit 0? No, it will not end with the digit 0 because it does not have 5, right? It should have both 2 and 5. So 6 raised to n will not end with 0 because 6, it does not have 5. It has 2, right? But it should have both 2 and 5. Then only you just have 2 and 3, so it does not end with a prime number. So here you can write it this as prime factorization of 6 is 2 into 3. And one thing I need to understand this. They've asked for 6 raised to n, right? You know that it is 2 into 3 raised to n itself, right? So for 6 raised to 1, it is 2 into 3 raised to 1. For 6 raised to 2, it is 2 into 3 into 2 into 3, right? When you write it like this, then you have 6 raised to 3. We have 2 into 3 into 2 into 3 into 2 into 3, right? So when you write for 6 raised to n also, it is going to be looking like this, right? It will not contain the number 5. So this is not going to end with the digit 0. I hope this is clear. This is the detailed kind of explanation. Okay, I hope it's clear. Now this is the sixth question. Explain why 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. This is the question. Okay, so I'll write here 7 into 11 into 13 plus 13, right? Here you can see that 13 is here also 13 is here, right? So I'll take one 13 common outside. When I take one 13 common outside, I have 7 into 11 plus 1. When I taken the 13 outside, so 13 ones are 13, right? So 13 into 77 plus 1, that is 13 into 78 you will get, right? So if you do the prime factorization of 78, prime factorization of this number is 13 into 2 into 3 into 13, right? This number is expressed in terms of prime numbers, right? Fundamental theorem of arithmetic. This number is a composite number, right? Composite number can be expressed in the terms of prime numbers, right? This is expressed in the terms of prime numbers, like more than one prime number, right? So this is a composite number. And the next one you have is 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5, right? We'll take the 5 outside, which is common. So we'll have 7 into 6 into 4 into 3 into 2 into 1. It's fine. If you don't write it also, it's okay. Plus, when you take the 5 outside here, it will become 1. So you have 5 into, when you multiply this 7 into 6 into 4 into 3 into 2, you will get 1008 plus 1. So we'll have 5 into 1009. If you try to do the prime factorization, you will realize that this is prime number, right? Again, this number is expressed in the terms of prime numbers, right? A composite number expressed in terms of prime numbers. So these both numbers are composite, right? I hope it is clear. Here you can write that. I hope this question is clear. If you're wondering, see, there's a honest question that comes in your mind that why can't we just, in the question they've given like this, right? Why can't we just, multiply this whole number, then add it with 5, then find the prime factorization and you can do. Yes, you can do like that. I mean, there is nothing wrong in doing that. Multiplying the whole number, then adding with 5 and finding the prime factorization and doing it, all fine. But it will be difficult. See, this number, whatever number you're gonna multiply and what you're gonna get, can be only expressed in this way. So it's a really time consuming process. Okay. So taking this 5 common outside and simplifying it at doing is much more easier rather than multiplying this, adding with 5, then finding the prime factorization and expressing it in terms of prime and all. It's a very time consuming process. It's really difficult. So you just take what's common here also. Here also you can multiply this and add it with 13 and all. But it's much more easier to take this thing common outside and do it in much more simplified way rather than calculating. And it's very time consuming. I hope it's clear what I'm trying to say. Now this is the last question of this exercise. This is the seventh question. There is a circular path around the sports field. Sonia takes 18 minutes to drive one round of the field, while Ravi takes 12 minutes for the same. Suppose they both start at the same point at the same time and go in same direction. After how many minutes will they meet again at the starting point? So there's a circular path. So let me draw a circle here. There's a circular path, and Sonia takes 18 minutes and Ravi takes 12 minutes, right? Consider this is the starting point. Both of them start at the same point, same time, in the same direction. So they're asking after how many minutes will they meet at the starting point. To meet at the starting point, when they complete one round, for Sonia it will take 18 minutes, right? What if just assume that Sonia is taking a second round? For 2 rounds, how many minutes will Sonia take? That is 2 into 18, right? We'll get 36. If Sonia is going once again for 3 rounds, if she takes to drive around the field, if it takes 3 rounds, so it is how many minutes it will take 3 into 18, right? Which is for 1 minute she is taking 18. Sorry, one round she is taking 18 minutes. For 2 rounds she is taking 36. 3 rounds 54. Can you see something similar or familiar in this? Isn't it just the multiples of 18? For 1 round she's completing, she take 18 minutes. For 2 rounds she's completing for 36 minutes, and for 3 rounds is 54. For Ravi's case also, for 1 round he's taking 12 minutes, right? For 2 rounds he will be taking 24 minutes, and for 3 rounds he will be taking 36 minutes, right? So it's going like this. So what do you find in this observation? These are multiples of 18, these are multiples of 12. Word multiple, is it making any sense? We can find LCM, right? We have to find the LCM of these two numbers to find out when they are going to meet after how many minutes. I hope what I'm trying to say is clear. So when you write the LCM of 18, you will get, I've already written the table. You might have already found out after how many minutes they might have met, right? But I'll write it. We'll do it according to the prime factorization method. 18 can be written as doing the prime factorization. You will get 2 into 3 into 3, and 12 can be written as 2 into 2 into 3. Now, what about LCM? LCM, what will you get? Here, 2 is common, right? And 2 with the highest power, right? There are two 2's over here. So, 3 is also common, but there are two 3's over here. So, we'll write two 3's. So, when you multiply this, will get 36 minutes. So, after how many minutes did they meet at the starting point? After 36 minutes, they met at the starting point. That means Sonia completed 2 rounds, and Ravi, after completing 3 rounds, they met at the same starting point. I hope what I'm trying to say is clear. So, this is the end of the video. Thank you so much for watching. Today we have studied about the fundamental theorem of arithmetic and how to find HCF and LCM using prime factorization, and also we have learned about we have solved exercise 1.1, and next video is about exercise 1.2. There is one more exercise of this chapter. We'll be solving that, and if you have any suggestions or feedbacks, please feel free to write it down in the comment box. And which chapter do you want next for me to explain? For that also you can write it down again in the comment box itself. So once again, thank you so much for watching. Happy learning.